All right, so module 14 OYOs. Number 1, 2 containers are filled with the same mass of both nitrogen and hydrogen gas. If the first container is significantly larger than the second container, in which container will the reaction be the fastest? Well, according to our module, we know that the more space there is, the less likely collision will occur between the molecules, and that's what's going to make the reaction work faster. So the smaller the container, the more likely, the more opportunity to collide, so more opportunity for the molecules to collide. So the answer is the smaller container. All right, 14.2. The muscles in an animal's body are run by chemical reactions. When these reactions occur, they contract the muscle, making it move. A biologist is studying a lizard and notices that when the lizard is in a cold place, it moves very slowly, but when it's in a warm place, it moves very quickly. Explain this observation in terms of chemical kinesis. So according to our book, chemical reactions are not happening very quickly when things are cold. So that would be the same in the muscles. So when the muscles are cold, the chemical reactions cannot happen quickly, therefore the muscles move slowly. But when the muscles are warm, chemical reactions are happening very quickly, therefore the muscles can move quickly. And that's your answer. A chemist does a rate analysis on the following chemical reaction, and it's this one here. He comes up with the following data. So here's our data table. What is the rate equation for this reaction? So you should have seen several of those in your book, but just before you did this problem, here's what we need to do is we need to compare what's happening between each of the concentrations and the reaction so we can fill out our formula. Our formula is R, which is the reaction rate, equals K, which is a constant, the concentration of A and its exponent, concentration of B and its exponent. All right. So first of all, we need to make our comparisons. So our comparison here, if we look at NO, which is here, when we go from trial 1 to trial 2, it multiplies, it doubles. So we say NO doubles, but what happens to the rate? The rate goes from this number to this number, and if you divide it out, it is times 4. So then we look at the trial 2 to trial 3 when the H2 changes, and H2 goes from 0.7 to 2.1, so it is times 3. When we compare the reaction rate, it goes from this number to this number, which is a times 3. And we're told in the text that when the numbers match, they cancel out. So we can look at our equation here. It's K, H2 to the Y, or H2 to the X, NO to the Y. And we can fill out, and it cancels out, meaning it becomes 1. So we have R equals K, H2, whatever concentration that is, and NO, the concentration of NO, we're going to square. So now we go ahead and pick one of these trials, and we're going to fill it out. So here's our number I always use trial 1 because it's the easiest for me to not get confused about. So here's my reaction rate for trial 1. There's K. I'm trying to figure out what that is. There's my concentration for H2, my concentration for NO. Remember, I have to square it when I do all my math. And I'm isolating for K, so my concentrations have to come over and get underneath the reaction rate. So there's my the way I lay it out. And it comes out to 0.09, 1 over molarity squared S, H2NO squared. So this is my reaction rate formula for this particular moment. Okay, 14.4. Ozone can be destroyed by certain pollutants, one being the nitrogen dioxide that is expelled from the exhaust of cars and planes. The reaction that governs this process is this. A chemist does the following experiment to determine how fast the ozone disintegration or destruction occurs. So that's his little chart with his 3 trials. What is the rate equation of this reaction? So remember, first thing we got to do is compare the concentrations of the 1 and the 2 and the reaction rate. So when I do these, I always look for the easiest comparison first. So it looks like my easiest comparison, when the O2 stays the same, I can compare with the NO2. If I compare the NO2, it doubles from trial 2 to trial 3, and so does the reaction rate. So that's times 2 times 2. So I know this is going to cancel out, and it's just going to be 1. Then we need to compare the concentration of O3. All right, so I need to look for where the NO stays the same, which is trials 1 and 3, but the O3 changes. So I'm looking at trials 1 and 3 to compare O3. So it goes from this number to this number, so it doubles here, but look what happens in the instantaneous reaction. It stays the same. So I have O3 doubling and the reaction rate not doing anything. So that's going to cancel this one out completely. So there's my original formula. R equals K, this concentration of A to the X, concentration of B to the Y. So now I'm going to start filling it out. R equals K, NO2, the concentration of NO2 to the X, O3 to the Y. Now I know that I can cross out O3 and NO2, which because they're the same number, they're going to go to 1. So it's we're just dealing with this R equals K and this concentration of NO3. So now I can fill it out using my chart, and I do the very first trial because it's easiest for me. So I fill in my reaction rate equals K and the concentration of NO2. Then I need to isolate for K, so I bring my concentration over to the reaction rate and cancel out whatever appropriate letters there are, because I need to keep my math equal to my letters as well, and I get 880 1 over S. And so my reaction rate formula is R equals 880 1 over S, the concentration of NO2. Okay, 4.5. The following reaction, 2PO plus Br2 equals 2PO-Br, is determined by experiment to be the second order with respect to PO and third order with respect to Br2. What is the rate equation? What is the overall order of the reaction? Well, here's my formula. R equals K, concentration of A to the X, concentration of B to the Y. The second order and third order is what those little X's and Y's are. So if I come over here, I can say R equals K, PO to the second, and concentration of Br2 to the third, because I'm looking at here and here, and it tells me second order with respect to PO. So I just plug those in. That's all we can do for the rate equation. And to find the overall order, which is what they're asking for, I just add the exponents up. So 2 plus 3 equals 5. So the overall order is 5. Okay, 14.6. The following reaction is determined to be fourth order with respect to C7H15Cl and 0 order with respect to NaF. What is the rate equation and what is the overall order of the reaction? Okay, so we're still using our R equals K, concentration of A to the X, concentration of B to the Y. I'm going to go ahead and fill that in. R equals K. Here's my first one with a concentration, and we know it's the fourth order because it says fourth order with respect to that. And then it says 0 order with respect to NaF. I just have to cross it out because of the 0 order of anything is 1. And so I finish it up and clean it up, and there's my rate reaction equation there. And because the overall order is just whatever the exponent is, that's 4, so the overall order would be 4. All right, 14.7. A chemist runs a chemical reaction at 100 degrees centigrade and determines the instantaneous rate to be 0.24 m over s. She decides to speed up the reaction by running it at 180 degrees centigrade. What is the new reaction rate? Okay, so here is our formula again. So it's R equals K, concentration of A to the X, concentration of B to the Y. We know from our book rate, the rates double every 10 degrees. So we have to go ahead and fill out what we know. Reaction rate is 0.24 m over s. That's what we have here. We know the initial is 100 degrees and the final is 180. So if we start here with our 0.24, we can actually chart it clear to our answer. And we know that this number doubles for every 10 degrees. So there's my 10, 20, 30, 40, 50, 60, 70, 80. Now we can actually list it out, times 2 times 2. We can list that all out. But for me and my dyslexia, it's easier for me to chart it. So when I get to the bottom there, I get 61.44 m over s. So that was my answer. My reaction rate has gone up to 61.44 m over s. The book says just 61 ms. All right, 14.8. In OYO question 14.5, you determined that the rate equation for the following reaction is this. If a chemist wants to runs this reaction at 30 degrees centigrade with reaction concentrations of 2.0 m, which is molarity each, and then runs the reaction again at 0 degrees centigrade with the same reactant concentrations, what will the reaction rates be in both cases? The rate constant for this reaction at 30 degrees centigrade is 1.25, 1 over m to the 4th times s. All right, so here's what we know. Our initial reaction temperature is 30 degrees centigrade. Our final reaction temperature is going to be 0. We know that we have our reaction rate here, so we can plug that in. We're going to go ahead and find the R. We need to find the R at the initial temperature. So we put our our formula is R equals K, concentration to A to the X, concentration B to the Y. So we put in, there's our K here, 1.25, 1 over m to the 4th times S. Our concentration for the first one, which is PO, is 2.0, and that is squared. And then we have the, for BR2 is 2.0, and that is cubed. So when we multiply that all the way out, we get 40 m over s. So we know that since we're going down, for every 10 degrees that we go down, we're going to get, this is going to be cut in half. So I went ahead and made my little chart at 30, 20, 10, and 0. And so each time I just cut it in half. And I got at 0, the reaction rate is going to be 5.0 m over s. And then why do the units in the rate constant include m to the 4th in the denominator? And it's because the answer needs to be calculated, the reaction rate needs to have units m over s. And so because we need m over s in our answer here, but we have m to the, we're going to have our exponents are 5 here. At the end of the day, we've got to have our reaction constant to get rid of most of those. So that's why those numbers get a little wonky, because we ultimately have to end up with m over s. And we can go through that and show you that mathematically, but at the end of the day, we're looking at the reaction rate. It needs to be molarity per second, and so we've got to work our math to make that work. All right, 14.9. I just want you to see who's helping me with my. How about that? She's trying to help me. All right, to catalyze the following reaction, solid platinum is often used. Is the platinum heterogeneous or a homogeneous a catalyst. So if this is solid platinum, and these are all gases, we know that the definition of heterogeneous is that it's just in a different phase as what is in the reaction. So solid platinum is a different phase than all the gases, so it's heterogeneous. Homogeneous means it would have to be a gas. Okay, 14.10. Two energy diagrams for the same reaction are presented below. Which one represents the reaction with a catalyst? According to our book, the catalyst is the one that takes away this big hump. So because it makes the reaction happen more readily. So it would have to be diagram A. It shrinks the start energy needed, which is also called the activation energy. And 14.11, identify the catalyst in the following reaction mechanism. So our step one, what we want to find out is whatever's up here that is added has to come out as a product at the end. So we look at the two that is added, and we come down here, and this one doesn't match exactly, but the 2I to the negative matches exactly. So that is our catalyst.